the matter of convergence for the Fourier series, and the question that naturally arises is that if you have a signal xt which is periodic in nature, does Fourier series is an exact representation of such a signal? That is, can you express xt as a sum of or a linear combination of complex exponential signals? Well, the answer is that in general this is true for an extremely broad class of periodic signals, okay? But it's not true for all the periodic signals, okay? I mean, it turns out that the Fourier series is not an exact representation of all periodic signals. There are conditions associated with when the Fourier series converges, or if you want to see in the other cases that does at any particular time, so let's say t1, okay, if I put t1, does this equality holds for all such signals, okay? And if it does holds, how good is, if it does not holds, how good is this approximation, okay? I mean, there would be signals xt that are periodic, for which we will find out that the Fourier coefficients ak are not finite, okay? If AKs are not finite, then this series is not going to converge. I mean, the question is this series convergent first for all periodic signals, okay? Is this convergent? And even if IKs are finite, the Fourier coefficients are finite, and you substitute this in, and then you, in the Fourier series expansion, you try to synthesize the Fourier series expansion, the series might not converge, okay? So we have to see the conditions that that are existing and that require, besides the periodicity of the signal, that are required for the Fourier series to converge, okay? So the historical perspective is that Fourier maintained that any periodic signal could be represented by the Fourier series. So although this is not quite true, okay, it is true that Fourier series can be used to represent an extremely large class of periodic signals, including a square wave and all other periodic signals which are of interest in practice. So to gain an understanding of the square wave example that we considered in the last video, more generally of the question of the validity of Fourier series representations, let us examine the problem of approximating the periodic signal by a linear combination of finite number of harmonically related complex exponentials. That is, by a finite series of the form. So what we are going to do is we are going to express our square waveform like we did in the last example, or more generally any signal with a finite number of harmonics. So n, capital N is the harmonics, okay? So this is not an infinite series. We are looking at a finite number of harmonics. So x and t is will represent xt with finite number of harmonically related complex exponentials, okay? It's a linear combination of finite number of harmonics, okay? So let E and T denote the approximation error, okay? That is between the original signal xt and x and t, which can be written as such. So then we go on defining the measure of this error, okay? How to minimize this error in some sense. So in order to determine how good any particular approximation is, we need to specify a quantitative measure of the size of the approximation error. The criterion that we will use is the energy of the error in one period. Okay, since we are talking of periodic signals, we are going to minimize this energy, okay, between the original signal xt, okay, this is the original xt, and then we have the approximation of that signal with a finite number of harmonics, and this is expression of for the Fourier series consisting of finite number of harmonics, okay. So so let's minimize this expression for finite number of harmonics, okay, and try to find out what the coefficients AKs are, okay. So you might want to take the partial derivatives of both sides of the equations with respect to AKs, and if you do that and you set the expression equal to 0, okay, after taking the partial derivatives. So let's take the partial derivative with respect to AKs. So you will find out that a particular choice for the coefficient that minimizes the energy in the error is this expression, okay? So this expression is very similar to what we derived in the previous video for the determination of Fourier coefficients. It is identical to the expression used to determine the Fourier series coefficient. So this coefficient is the one that minimizes the energy between the original signal xt, that is periodic, and its representation in terms of Fourier series with a finite number of harmonics. So this minimizes the energy criterion that we have described. Okay, so thus if xt has a Fourier series representation, the best approximation using only a finite number of harmonically related complex exponentials is obtained by truncating Fourier series to the desired number of terms. Okay, so as you see, if you go on increasing the harmonics, new terms will be added and your error is going to be decreased. So in fact, xt has a Fourier series representation, then the limit of E of n as n approaches infinity becomes 0. So as we are going to add more and more harmonics, as we are going to increase the number of harmonics, your representation will be more and more close. It get more close to the original signal xt, and the error thus reduces to 0. Okay. So now let us turn to the question of when the periodic signal xt does in fact have a Fourier series representation. So now, of course, for any general signal, we can attempt to obtain set of Fourier coefficients. However, in some cases, Fourier coefficients integral may diverge, so that AKs are not finite. So that is the value we obtain for some of the AKs may be infinite. Okay, so this Fourier coefficients for all Ks, the integral diverge, and you don't have a finite value of the Fourier coefficient. Moreover, even if all the Fourier coefficients obtained are finite, when these coefficients are substituted into the synthesis equation, the resulting infinite series may not converge. So even if you're going to substitute this, if they are finite, you're going to substitute in the synthesis equation of Fourier series, the series might not diverge, might not converge. Okay, it can diverge. Okay, so what are the conditions that will justify the fact that the Fourier coefficients are finite and the series is convergent for those finite coefficients? Okay, so let's see what those conditions are. So fortunately, there are no convergence difficulty for a very large class of periodic signals. But for example, every continuous periodic signal has a Fourier series representation for which the energy En is in the approximation error approaches 0 as n goes to infinity. This is also true for many discontinuous signals. Since we'll find it very useful to include the discontinuous signals such as square wave in our discussion, it is worthwhile to investigate the issue of convergence in a bit more detail. Specifically, there are two somewhat different classes of conditions that a periodic signal can satisfy to guarantee that it is represented by Fourier series. Okay, so the first condition is there is one class of periodic signals that are representable through Fourier series is those signals which have finite energy over a single period. So you see, if the energy of signal is finite, then this should imply that your Fourier coefficients are finite. Okay, Fourier coefficient will be finite because this also implies absolute integrability. Okay, and you'll see that with absolute integrability, if it exists for a signal over one period, the Fourier coefficients are finite. Okay, the absolute value of the Fourier coefficients are finite. So when this condition is satisfied, we are guaranteed that the coefficients obtained are finite. Okay, this is the first. So furthermore, let x and t be the approximation of xt obtained by using these coefficients. Okay, up until the nth harmonic. Then this is the representation of the signal with n harmonics in terms of Fourier series. Then we can guarantee that the energy in the approximation error converges to 0 as we are adding more terms. That is, we define as such the energy criterion as the what we are doing is we are trying to minimize the energy between the energy of the error, that is the error is between the original signal and the finite number of harmonics that are representing in Fourier series the signal xt. So we're minimizing that energy, and that minimization doesn't mean that xt and its Fourier series are going to have the same values at any particular instant in time. It simply means that the energy between these two representation is zero. Okay, so what it says, this does not simply implies that signal xt and its Fourier series representation are equal at every value of t. What it does say is that there's no energy in their difference. Okay, there's no energy in their difference. So if you have a finite energy signal, then this representation, if you're going to represent this by a finite number of harmonics, a signal xt, okay, then the error goes to zero as n approaches infinity. That's the idea. Okay. So the error has been minimized. There is no energy difference between the Fourier series representation of the signal with n harmonics and the original signal. Okay, so the energy of the error has been minimized. There is no energy in their difference. So this type of convergence, and this is only valid when xt is finite energy over one period. So this type of convergence guaranteed then when xt is a finite energy over a single period is quite useful. In this case, the difference between xt and its Fourier series representation has zero energy. So since physical systems, they respond to signal energy from this perspective, xt and its Fourier series representation are indistinguishable. So for all, since physical systems are responding to the energy signals, okay, signals having finite energy, if over one period they have a finite energy, well, you can go ahead and use their Fourier series representation, and this representation becomes indistinguishable with the original signal, okay, if it is finite energy in one period. So because most of the periodic signals that we consider do have a finite energy over a single period, they have Fourier series representation. So this is a good enough condition for the existence of Fourier series for such signals which have finite energy or they have absolute square integrability that is finite. So moreover, an alternate set of conditions developed by a German mathematician P.L. Dirichlet and also satisfied by essentially all of the signals with which we will be concerned guarantees xt equals its Fourier series representation except at isolated values of t for which xt is discontinuous. So at these values, the Fourier series having infinite number of harmonics and converges to average value on the other side of the discontinuity. Okay, so if you have a discontinuity like this, then if you have a lower number of harmonics, well, that could be like this, few harmonics, and then the signal goes like this. So this will be the Fourier series representation. Okay, and you'll see that discontinuity, this will be the half value of the signal on either side. Okay, either side of the discontinuous. For example, this is the point, and then this is the point of the signal at and before, well, before and after the discontinuity. So the point that Fourier series is going to take as discontinuity will be the average of the 2 points. Okay, so at these values, the Fourier series having infinite number of harmonics, and converges to the average value on either side of the discontinuity. So you will see later on that if you go on increasing n, these ripples they vanish. Okay, the energy becomes indistinguishable, and again they might vanish. But even then, at discontinuity you will have the average value, but then there will be an overshoot. Okay, it doesn't matter if n goes to infinity, you still have an overshoot, which is about 9% of the maximum height of the signal at the discontinuity. So that means at discontinuity, the Fourier series does not exactly represent the signal, but this overshoot is a peculiar phenomena which goes by the name of Gibbs phenomena. Okay, it's famous by the name of the mathematician who showed that this is indeed the case. Even if you go on increasing the harmonics, well, you still have the overshoots and the undershoots, which are about 9% of the maximum amplitude of the signal. You cannot get rid of that. Okay, you might improve this part. The ringing the high frequency ripples their energy will be very small. That the energy might go to zero, but these overshoot and undershoots are there at discontinuity. Okay, so that happens in Fourier series approximation. We're going to discuss that in a while. So let's first talk about the Dirichlet's conditions that this German mathematician derived for the existence of Fourier series. So the first condition is that this is just a consequence of the finite energy, that if a signal is finite energy, it's also absolutely integrable. So over any period xt must be absolutely integrable. So if that is the case, if this is the situation, then as with square integrability, this also guarantees that each coefficient ak will be finite. Okay, because if you're going to, okay, if you take the magnitude of both sides, you take the magnitude inside the integrand, then there's an inequality. Okay, because all the terms becomes positive. Okay, so if you take then the product of the modulus of both sides, like the magnitude of both sides, exponential magnitude is unity, so you're left with this expression. Okay, and if the signal is absolutely integrable, if this quantity is less than infinity, then for a finite period capital T, the magnitude of the Fourier coefficients is less than infinity. That is, the magnitude is finite. So this is a finite for a absolutely integrable signal over one period implies that the Fourier coefficients are finite. Okay, this is the first condition. So now a periodic signal that violates the Dirichlet's condition is 1 over t. This is again a finite signal. Okay, with period 1, you see over there here, this is 1 over t, but it's not absolutely integrable. Okay, I mean, what it means is that the area is not finite under the curve at a point where t equals. So this area is becoming extremely large. I mean, you cannot integrate this. So around t equal to 0, although this is periodic. This is periodic with period 1, but then this area is not finite. Okay, you cannot absolutely integrate xt. If that is not the case, then your Fourier coefficients are not finite. Therefore, the Fourier series diverges; it doesn't converge. So that's the first condition, that xt should be absolutely integrable. Okay. Then the second condition is that in any finite interval of time, xt is of bounded variation. That is, there are no more than a finite number of maximas and minimas during any single period of signal. Okay. So for example, if I take a signal like this, it's a sort of waveform, and this happens to be my period. Call it t naught. Okay. And in this period, you see, this is one period. Okay, and this pattern is repeating. So this is one period. This is one period. This is what I'm considering right now. So over this period, I just have one maxima. Okay, I just have one maxima. If you want to consider the other period, for example, okay, let's consider this period t naught. Another. Let's shift this. So over this interval, you have just one minima again. These are finite maximas and minimas that you have in one period. The Fourier series for such a periodic function xt will exist and will converge if there are finite number of maximas and minimas over the single period of the signal. Okay. So, but at the same time, an example of the function that meets condition 1, not condition 2, is this signal. Okay, what it means is that this signal is absolutely integrable. It is absolutely integrable over the period capital T, which is 1. Okay, from 0 to 1, this you can take the absolute integrability of the function, and you can show that this is less than unity. But if you look at the plot of this function, this however have an infinite number of maximas and minimas and zeros. Okay, so what happens is that, for example, then if this is the period, okay, for one sine wave, then for the next sine wave, which is over here, this period drops by the fraction. Okay, and then the next period is still a smaller fraction, and this continues. Okay, so which means that there will be infinite number of maxima and minimas, and for such signals, although they are absolutely integrable, there are infinite number of maxima and minimas. Okay, so for over one period, so over from t equal to 0 to 1, you cannot count the number of maxima and minimas. Okay, this is maxima, this is minima, and then you go on counting. So how many maxima are there? Well, it just bunches up together and so on and so forth. It doesn't end. So the number of maxima and minimas are infinite. So you cannot have a convergent Fourier series for that. Then condition 3 is that in any finite interval of time, there are only a finite number of discontinuities. Furthermore, each of these discontinuities is finite. Now consider this signal xt. You see there are many jump discontinuities. So as for example, from well, the first thing to see is that this signal is absolutely integrable. Isn't that right? I mean, x of t, its area, it's easy to see that is less than 8. Okay, I mean the absolute integrability over one period, which is 0 to 8, will be less than 8. Okay, so an example of this function violates the condition 3 is illustrated in the figure below, and the signal is of period 8. It's composed of infinite number of sections, each of which is half the height and half the width of the previous section. So the area under one period of the function is clearly less than 8. So it is absolutely integrable. However, there are an infinite number of discontinuities in each period violating the condition 3. So you see from 0 to 4, this will be 4. Okay. There's a discontinuity that occurs, and then after that your the height of the signal becomes half, and then at 6, okay, this still takes a value of 1/4. Okay, then at 7, so as the time progresses up until 8, then 7.5. So at 7, this will be 1 over 8. Okay, then 7.5, 1 over 16, and it continues. Okay, after 7.5, it will be 1 over 16. So a periodic signal with period 8 that violates the differential condition. You see, for 0 to 8, the value of xt decreases by a factor of 2 whenever the distance from t to 8 from decreases by a factor of 2. That is, xt is 1 for 0 to 4. It is halved for 4 to 6. Okay, so it is half from 4 to 6. And then thereafter 6, from 6 to 7, it is 1/4. Okay. So these are all discontinuities in the function. And from 6 to 7, so this is 1 over 4 from 6 to 7, and then xt is equal to 1 over 8. Over here, this becomes still 1 over 8. This is 1 over 8 from 6 to 7. And then after 7.5, from 7.5 to 7.75, it will be 1 over 16. Okay. So there are many discontinuities. Although the signal is absolutely integrable, the condition 1 is satisfied. But the number of discontinuities are not finite. Okay. So this situation, this signal does violates condition 3, and the Fourier series is not convergent. Okay. The discontinuities have to be finite in a signal. For example, this is a square pulse. Okay, and this is a square pulse, and if this is my one period, okay, and this continues on either side, if I define this as one period, the number of discontinuities are finite. Okay, this is one period, then there is one discontinuity over here, second occurs over here, the third occurs over here. Okay, so you can count the number of discontinuities, 3 discontinuities. Okay, but over here, well, it keeps growing on. Okay, 7.5, 7.75, and then even then you have it. So each that as the time is progressing, first of all, the amplitude decreases by a factor of 2, and then as the time is progressing, and that's also shrinking by the factor of 2, the discontinuities, they keep on increasing. Okay, they keep on increasing. All the signal is periodic, but you cannot go on having infinite number of discontinuities. So this violates the Dirichlet's condition, and therefore the Fourier series is not convergent for such pathological nature signals. Okay. So for a periodic signal with finite number of discontinuities in each period, the Fourier series representation equals the signal everywhere except at the isolated points of the discontinuity, at which the series converges to the average value of the signal on either side of the discontinuity. Okay, so for example, if you have a finite number of discontinuities in the signal like this, then these points, the Fourier series is going to take the average value of the signal on either side of the signal. Okay, so it will be something like, if you have a very large number of harmonics, something like this. So it does represent a very good, it gives a very good approximation to the signal. But then how much ripple is there, and how much ripple is there, and how well does this approximate the square signal depends on the harmonics, number of the harmonics that you're using in representing the periodic signal with the Fourier series. Okay, so as n approaches, as n becomes infinity, this discontinuity, the Fourier series is going to converge, and this will be half the value of the signal. Okay, on either side. So for example, after the discontinuity and before the discontinuity, whatever these values are, this value will be the half of the two values, this one and this one. Okay, so in this case, the difference between the original signal and its Fourier series representation contains no energy. So in fact, this is convergent. Okay, so the Fourier series does exist because the number of discontinuities in one time period, for example, over here to here, is finite. So this is one time period. Number of discontinuities you can count are 3. So for one time period, this is finite. Okay, this one discontinuity over here, one is over here, 3. So this is 3. These are 3 discontinuities. 1, 2, and 3. There are 3 discontinuities. So consequently, the two signals can be thought of as being the same for all practical purposes. Specifically, since the signals differ only at isolated points, the integrals of both signals over any interval are identical. For this reason, the two signals behave identically under convolution and consequently are identical from a standpoint of analysis of LTI systems. Therefore, if you apply the signal xt itself or its Fourier series representation, the LTI system output will be the same. Okay. So, for example, over here you see this shows the convergence of this figure shows the convergence of Fourier series representation of a square wave, okay, which has a finite number of discontinuities. The Fourier series exists, but at isolated points where there is discontinuities, the Fourier series is going to take the average value of the signal. Okay, so this is the average value of the signal it's going to take at the discontinuity. This is the first harmonic. You can see this is just a sine wave, and as you go on increasing, so this is, you add another harmonic, that is the third harmonic. So n equal to 1 and n equal to, so for if you compare this for n equal to 1 with n equal to 3, there are 2 signs. Okay, again this is the average value. Okay, but this representation becomes better as you go on increasing n. But there is a high frequency ringing, and this high frequency ringing is still there if you go on increasing the add the number of more terms, more harmonics. So, but this does illustrate a very peculiar phenomena, strange phenomena, which occurs at the jump discontinuity, and this peak is about 9%. Even if you go on increasing and very large number of harmonics, even if you have n equal to infinity, even then this is about 9% of the maximum height of the signal, and this is known as the Gibbs phenomena. There is an overshoot and then there is an undershoot. So this is plus minus 9%. Okay, and you cannot avoid this, although this ringing is gone. This ringing that you look over here, that you're looking over here, is gone as you go on and increase the number of harmonics. So you can say that a Fourier series is representing the square waveform at every time instant t. But at jump discontinuities, there's an overshoot and undershoot, which is undesirable, and there is nothing that can be done about that. Okay, so this is Gibbs phenomena. An illustration of this. So this figure shows an illustration of Gibbs phenomena. Here we have depicted the finite Fourier series for approximation of several harmonics n.